It's my pleasure to make the first introduction today. So we've had the joy of hosting Sumiko and Takamichi for the last year at the Transport Safety Research Centre, which is based in the School of Design and Creative Arts. So to introduce our first speaker today then, Sumiko received her PhD in engineering from Tokyo Institute of Technology in 2012. After serving as an assistant professor at Kanagawa University as an assistant professor and then associate professor at Shimbura Institute of Technology, she's then become an associate professor at the School of Engineering and the Institute of Science in Tokyo, where she's been since October 2024. And then they came to visit us from August 2025 and have been here with us for the last year. So her research spans the interdisciplinary fields of edge computing, networks for AI, and traffic analysis based on mathematical optimization, including queuing theory and game theory. In her recent research, she's worked on the design of load balancing methods for edge computing to support autonomous driving, which hence the engagement with the Transport Safety Research Centre, as well as the development of cooperative participation incentive mechanisms for safe driving assistance between vehicle-to-everything systems, with the aim of realising the next generation mobility and improving our smart cities. So I will welcome you to the floor and say thank you very much for joining us for the past year. Okay. Thank you.
Thank you, Ashley, for the kind of introduction. So my name is Sumiko Miyata from Institute of Science Tokyo. It is a great honor to present at the wonderful seminar. And the title of my presentation is Incentive-Driven AI Networks for Future Road Safety. So I am currently with the Transportation Safety Research Center. So first of all, I would like to say a big thanks to my host professor, Ashley Fitness, and everyone here. So Ashley is a professor here at the TSRC. She works on human factor at the human factor and sleep science to improve the transportation safety. So if you want to know about the TSRC more deeply, so please check the QR code. So they conduct the wide range of great research for the transportation safety. So everyone at TSRC was very kind to me. So thank you for inviting me to the many wonderful events. And I also want to thanks Andrew and because for the working with me. And I am glad to have research collaborators and in the SDLC and the computer science and the civil engineering. And yeah, thank you so much. And I also want to thanks yourself because are working to me. Yeah, I could have the good opportunity to attend many IAS seminars, and I was able to meet many people from the different area. So thank you very much, and I am very happy that I spent this year at the Lahore University. So let me introduce myself. My name is Sumiko Miyata, and in Japanese it is written like this. And yeah, I'm from the Institute of Science Tokyo, and it is a new name created in 2024 after the merge of Tokyo Institute of Technology and Tokyo Medical and Dental University. This is a very oldest building in my university. And from the last year, I stayed as a visiting academic for the 1 year at the Transportation Safety Center, SDA, Lahore University. So as you know that the UK latitude is very different from the Japan latitude. So I found that it is very comfortable, especially the summer season. Yeah, I like this. Yeah. Yeah, and my research interest is information network infrastructure for the smart city by using the queuing theory and the game theory. So, why is studying the network infrastructure necessary? City as a service in a smart city means people can choose city service like a smartphone application, such as this kind of the figure. So, in this case, we need network the key technology to future cities. And massive human movement generates the huge data traffic, and the autonomous mobility requires high safety and security. But what happens if we don't have a proper network infrastructure with the data control? There are some root error and robot shutdown, and without the security, robots or cars may go out of control. This is why a reliable network infrastructure is essential. So this is my goal of the network structure. Let's consider that there is some the traffic accident and the traffic jam occurred in the situation. So to solve this kind of the problem, we need to consider the three topics. The topic A is a monitoring, and the topic B is a high-speed processing, and the topic C is a protected data. So by using this kind of technology, we can improve the route efficiency for autonomous vehicle and ensure the road safety. So in this presentation, I talk about the two topics, the topic A and the topic B. So first, I talk about the topic A as a star, yellow star. And so this work is a collaboration one with Lahore University and the Chiba Institute of Technology. So this key technology of the intelligent transportation system is a vehicle to everything technology, which means that connects vehicle and everything. And as you know that I focus the cooperative perception technology of the V2X. As you can see that, for example, the two the camera and each camera have there are two terminal, the car and the roadside unit. They have the each camera. By using this situation, we can merge the sensor data. By using the cooperative perception, we can decrease the occlusion such as a blue area, and we can increase the AI recognition accuracy. But let's consider about the situation. So I think that the yellow car and the RS roadside unit company are different. So to realize this kind of the system, we need to consider the heterogeneous organization. So to keep the suitable the system, it is important to introduce the intense incentive mechanism. So there are many kind of the previous incentive mechanism. So generally, we can consider the trade-off between the data provider of the camera and the buyers. So in this situation, we can use the game theory approach to the balance data value and the incentive. So there are many research paper, but there is no proposal of incentive mechanism with dissatisfaction. So what is dissatisfaction? So as you can see that this means that the incentive value for each sensor is very low, such as blue player. So in this situation, this blue player may depart from the system because this incentive is very too low. But if this dissatisfaction decrease, all sensors can continue to the provided data, so we can improve the long-time AI recognition accuracy. So in my presentation, in my studies goal is the improvement of the long-time AI recognition accuracy considering dissatisfaction. So assuming system is here, we assume that two kinds of sensors and the 2D camera and the 3D LiDAR cameras are located to vehicle and RSU. And by using the cooperative 3D, I merged this kind of data. And finally, the server delivers the appropriate incentive every sensor. And in this use case, we want to consider the sustainable monitoring system to improve the road safety. So by to achieve this the goal, I try to model the incentive mechanism by using the cooperative game theory. So the cooperative game theory can derive the good incentive by using the utility function. So we need to define the utility function in every the problem. In this study, I try to define the utility function as here. So this utility function is used payoff by the AI recognition accuracy. So by using the utility function, we can derive the incentive. But in real system, so sometimes we cannot easily find the AI recognition accuracy for some groups. So we need to estimate the utility function value for the all group. So in this study, I try to do the tensor train decomposition. So this is our incentive value. So incentive value is for I used the Nucleolus. Nucleolus means minimizing the worst dissatisfaction among the users. So dissatisfaction, the definition is here. So for example, so as you can see that the blue group is a whole group member, and this member can get the utility value of the 50. And the red group is the small groups, the two members. So this group can, and if the small group member can get the utility value of the 30, in this situation, the small group want to cooperate with each other. On the other hand, if the small group can get the utility value of the 60, in this situation that they do not want to cooperate with each other. So by using this satisfaction, so we can get the nucleus. And this advantage is easier to maintain the cooperative relationship. So what is a long-time AI accuracy in this presentation? This means a group with a non-negative excess, the dissatisfaction occur with equal probability. So the parameter setting is here, and by using the parameter, we compare with the long-term AI accuracy with the method. So this is a final result. And the best one is Shapley value. Shapley value is a very famous the value by using the cooperative game theory. And the value is fairness incentive value. By using the Shapley value, some group have the dissatisfaction. So the long-time accuracy is a little low. On the other hand, Nucleus, our method incentive value is very high. So our method can get the highly effective for the both sustainable and maintain AI accuracy. Okay, so the next topic. So the topic B is high speed processing. Okay, so let's see the video. Okay. So this is the 3D point cloud data, and we want to consider the city digital twin. So the city digital twin, by using this kind of 3D point cloud data, we can create the city digital twin. But we need to have the continuous monitoring data collection to create this kind of the city digital twin. So, and to realize this kind of the city digital twin, we need to consider the mix of the inference and the training task. So to reduce the communication network load, so we need to assume that the edge computing, such as the green area, and but we want to reduce a lot of the network traffic, so we try to apply to the federated prompt learning. So the federated prompt learning is the sharing only the prompt. So what is a federated prompt learning? Federated prompt learning reduce overhead by sharing only the prompt, not full model. As you can see that the left side is a traditional federated learning, and this system is need to extend the full model, so very heavy traffic load. On the other hand, the federated prompt learning is only the exchange of the very light the prompt. A photo of a cat is a very light model. So the by using the FPL, so we can omit ignore the traffic load between the cloud and the edge traffic link. So the initiation we can focus of the offloading between the device to decrease latency. So what do we need to consider for offloading between the edge servers? So first step, we need to consider the characteristic of the each task. So inference task is a very, very high arrival rate and a short processing time. And for example, the inference task is a real-time pedestrian detection on a junction. And on the other hand, the training data is a very low arrival rate and a long processing time. And for example, so this training data is updating of the AI model. So there are few the previous off-roading in this area. So, but in this previous off-roading method, there is no communication overhead. This means the time to take to the send task data to the network link, such as the red arrows. So in this study's objective is minimizing the delay time of the training task while the delay of the inference task maintains. So to derive the delay time, I want to use the queuing theory. So do you know the queuing theory here?
No.
Oh, okay. So the queuing theory is a very, very powerful tool to calculate the waiting time and the number of waiting people. And this is the only three. We only use the three parameter to calculate the evaluation value. For example, so in this study, the key parameter is only here. The average arriving rate, average processing rate, and the traffic network load. By using this the simple parameter, we can derive the delay time by using the queuing theory. And in this presentation, we assume the interrupted enable priority control model by using the queuing theory. So in this the study, I assume that inference task is a high priority and the training task is a low priority. So we can derive the task delay time for each offloading control. So this is the waiting time equation for the very traditional textbook. So it's a very simple equation by using the lambda and some b. So this is the average value. And this meaning the pink term is a waiting time and the orange line is a server waiting time. So by using this, the sum of this term, we can derive the waiting time. And I want to apply to the offloading system to this kind of the equation. This is a delay time with offloading system. This is a little big one, but almost the same. And the additional point is a green one. So as I mentioned, I want to add the communication overhead so that we add the communication overhead term. And the pink and the orange is almost the same as the traditional textbook. So by using this kind of the equation, we derive the optimal strategy by the calculating by the delay time. Okay, so this is a parameter, and we assume that system that we use the vision language model CLIP, and I want to explain about that. The next presenter, Takamichi, also used the CLIP, so that he also explained more deeply, so that I omit this kind of one. And I also assume the FPL, and the task processing time is here, and the objective function is here. And the baseline is a plot that not consider the offloading inference task. Okay, so this is the final result. So the evaluation value, the achievement rate of the acceptable delay. So this, as you can see that our method can achieve the very high rate acceptable delay in the inference task 100%. And average delay on the inference and the learning is almost the same compared to the previous method. So by using our method, we can achieve that the many inference tasks can be performed by considering the communication overhead. Okay, so the conclusion and thank you. And we show how can we build an incentive-driven AI network for the future road safety. And first, as a topic A, I propose a nucleus-based incentive mechanism. And as a topic B, I designed the task-aware offloading method by using the queuing theory. So thank you for your attention.
So thank you very much, Sumiko, for that presentation. Very interesting. As Ashley said, Sumiko and Takamichi have been with us for almost 1 year now, and it's been our pleasure to host their visit. And I know they've made lots of friends within the School of Design and Creative Arts. It's my pleasure to introduce Professor Takamichi Miyata to the Institute of Advanced Studies today. Just a little bit of background on Takamichi. He received his DEng degree from Tokyo Institute of Technology in 2006 and served as an assistant professor there until 2012. He joined Chiba Institute of Technology as an associate professor in 2012 and has been a professor in the Faculty of Advanced Engineering since 2016. He's been a visiting academic with us from August 25 to this year, and his research spans image processing, computer vision, and computer network. Recent work explores zero-shot approaches using pre-trained generative models for tasks such as colorization and inpainting, as well as parameter-efficient network design for image denoising. He also works on cooperative perception for V2X systems, and he received the Institute of Electronics, Information and Communication Engineers Excellent Paper Award in 2014. And as you can see, the title of Takamichi's presentation is Multimodal AI that understands driver behavior without training data. Thank you, Takamichi.
Thank you. Thank you, Andrew, for kind introduction. And good afternoon, everyone, and thanks for having me today. So my name is Takamichi Miyata, as shown in here, and I'm from Chiba Institute of Technology, and I'm currently a visiting researcher here at the Transport Research Safety Research Center. So today I'd like to talk about a multimodal AI that can understand driver behavior without any training data. So first, I'd like to express my sincere gratitude to Professor Andrew Morris for hosting my academic visit here at Loughborough. And this visit has given me something quite rare, a chance to connect my research background, AI and image processing, directly with transport safety research. And I also gratefully acknowledge financial support from the Kajima Foundation and the Telecommunication Advanced Foundation. So let me introduce myself a little. So I am a professor of Chiba Institute of Technology. So now Chiba, I imagine many of you have no idea where the Chiba is, and that's okay. So it's the prefecture right next to Tokyo to the east. And this cute character is Chiba-kun. He's the official mascot of Chiba Prefecture. He got his shape because the prefecture itself looks a bit like a dog. And so does he. And Chiba-kun is surprisingly useful. So because his body is a map of Chiba, so there people there use him to show where they live or work. So, for example, my university sits right here around Chiba-kun's chin. So maybe many of you are, already memorized where I work for. Yeah. So my own office is this floor of this modern-looking building. And in clear day, we can see the Mount Fuji from my office. Yeah, that's the floor. Yes. So now my background is in image processing. I haven't really worked on transport research before. So what I like to do today is talk about what became possible when we bring those two worlds together. The technical content is based on our research paper. So this is a joint work with Sumiko and Andrew. So let me start with the motivation. So according to the WHO, about 1.35 million people die in road traffic collisions every year. And distraction is one of the major contributing factors. A driver talking on the phone, texting, looking at the back seat. Each of these takes eyes, hands, and or mind away from the road. The engineering idea is simple. An in-cabin camera watching the driver. An onboard AI system, what we call here edge AI, meaning the computation happened inside the vehicle, not in the cloud. And it analyzes the image. And if the driver looks distracted, the system can give a warning before the dangerous situation develops. So the pipeline is very simple. The hard part, as always, is making the AI actually work. So this is what the rest of this talk is about. Okay. So the standard approach in AI is supervised learning. So concretely, our task is to look at one in-cabin image and sort the driver's behavior into one of about 10 or more categories. So safe driving, texting, talking on the phone, and so on. So to do this, we collect many images of drivers, label each one, and train a model on them. But this has two problems. The first one is cost. Collecting and labeling large-scale in-cabin data with the SCAL approvals is expensive. The second is fragility. So a model trained on one dataset often performs poorly on another dataset with different drivers, vehicles, or camera angles. So this is called a dataset shift. And it remains one of the hardest problems in applied AI. So the question becomes, can we skip the data collection and training entirely? So this is my idea of zero-shot detection using pre-trained multimodal vision language model AI. Okay, so the problem is at this point, you may be thinking, well, wait, what is zero-shot? What is multimodal? What is the vision language models? It's fair enough. Before going further, let me spend a few minutes of 3 questions. What is zero-shot inference? What are vision language models? And why should they help with driver monitoring? So if you follow these 3 ideas, the rest of my talk will be very easy. Okay, so let's start with what is zero-shot inference. So zero-shot inference means using a pre-trained model to solve a new task without any additional training for that task. So I think you already know an example, it's ChatGPT. So when you ask ChatGPT, like, explain this theorem for secondary school students, or classify this review as positive, negative, or sarcastic. So yeah, so nobody trained ChatGPT specifically for your request. It draws on broad knowledge learned from enormous amounts of data and simply follows your instruction in plain English. So one important clarification is zero-shot does not mean the training at all. The model was trained massively, only once, in advance on general data. So zero-shot means zero additional training for the specific task we care about, in this case, dissatisfaction detection. So why is this attractive for driver monitoring? Because it means we no longer depend on a specific data set. So those data sets may be small, expensive, and biased towards particular drivers, vehicles, or countries. Okay, now let's go on to the what are vision language models? So the representative example is CRIP. I think you already see the name in the Sumiko slide. And this is released by OpenAI at 2021. And here's the intuition. So please imagine someone who has browsed millions of photos together with their captions until they deeply learn which words go with which images. Click is that kind of person. So in mathematical form. So it turns both an image and a text into vectors in the same latent space. So that matching meaning land cross together of those vectors. So that enables simple matching game. The one shown on the right. So here we have our dog image and take an image, prepare candidate captions. So in this case, we prepared the caption like photos of plane, photos of cat, photos of dog. And pick the closest one from those captions by using quick. So that is a prediction. And here is the remarkable part. To recognize something new, you don't retrain anything. You just change the caption, the prompt, we say. The next prompt, the text prompts are the classifier. So one model, so many tasks just by editing text. So, okay, so the obvious next question is, can we just take a pre-trained script and with 10 captions about driver's behavior and call it a day? Unfortunately, the answer is no. Direct use does not work well. I will show you later. But the next problem is, can we fix it? The answer is yes. And the fix requires no training at all. The rest of this talk is about why Clip fails for this task and how to my simple geometric operation repair it. So this is not just our observation. There is a prior work. This table is adapted from Hassan and his colleagues. They already tested CRIP for zero-shot distracted driver detection. And look at the top row. So naive zero-shot CRIP on this benchmark. In this case, top one accuracy is around 50 to 66%. So compared to this, to the low, the method is task-specific training. They reach 80 or 90% and above. So zero shot is very convenient, but the accuracy gap is still large. The question is, what exactly reads CRIP here? So why does a model that recognizes dogs, planes, cats, so struggle to tell talking on the phone and texting on the phone? So our key insight is that there are two things get tangled together in CRIP feature space. So we call them two entanglements. So entanglement number one is on the image side. When CRIP looks at an in-cabin photo, the feature vector is dominated by the driver's appearance, so their identity, the gender, the age, crossing. So in other words, the model pays more attention to who is a driver than to what they are doing. For driver monitoring, this is exactly backwards. So we don't care who you are, we care whether you are texting them. So entanglement number two is on the text side. So our behavior captions, in this case, we have 10 captions, are linguistically very similar. So their feature vectors point in nearly the same direction. And the matching game becomes a coin flip between neighbors. So we propose the method to fix this two problem without any training data. So please keep the phrase in mind, who, not what. Okay, so let me show you this problem in visual way. So this figure is so-called a T-SNE plot, and you don't need to know how it is made. So just read it as a map. And each dot is one image or one caption text. And dots that are close on the map have similar feature vectors inside CRIP. So what should this map look like? Ideally, there must be 10 islands, one per behavior, with the matching caption sitting on the middle of each island. That is the ideal case. But what do we actually have? We can see here, look at the green circle. There's the two green circles. And these tight clusters are not behaviors. They are individual drivers. So all the image of one driver huddled together, whatever he's doing. So it is who, not what. And the red circle, you can see the red circle on the middle. So it is those tiny nodes is all 10 captions. So all 10 prompts goes in only one place. So the vectors were very similar. It's too similar. So this is an overview of my proposed method. We have proposed two components called DAD and TEO. I will explain it later. And the DAD is treating on the image entanglement, and TEO is for the text entanglement I already showed before in visual way. The first is the image side, and in this illustration, blue circles are driving safely, and yellow triangles are touching his or her hair. The top cluster is driver number 6, and the bottom cluster is driver number 10. So notice the problem. The clusters are organized by driver, not by behavior. So here's a fix. I propose that it is almost embarrassingly simple. So for each driver, compute the average of all the features vectors. Think of this average as the driver's appearance signature, the part that says who they are. regardless of what they are doing, then simply subtract it from those drivers' vectors. So, and what remains after subtraction is a deviation from the driver's average. And that deviation is precisely the behavior. So look at the right-hand side. After subtraction, blue gathers with blue, yellow with yellow. So the cluster now means what, not who. So one particular node is computing these are averages needs only unlabeled images of each driver. So which an in-cabin camera collects automatically. So just by recording, there's no annotation, no training needed. So second, we are trying to tackle these text problem. So as you can see, our 10 captions share the most of the words. It's like an image of person blah 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 while in the driving. So the vectors point in almost the same direction. So imagine that there's 10 signposts at a junction, and all point roughly north. So it's very useless for navigation. So the TEO rotates these vectors point to different directions. In mathematical terms, we make the vectors orthogonal. But there's a subtle part. So we cannot just capture them randomly because each vector still has to mean what its caption says. So we look for the orthogonal arrangement that stays as close as possible to the original vectors. So for those who enjoy the mathematics, it is a metric projection onto the Schrieffer manifold, and we can compute it with our simple SVD, singular variable decomposition. For everyone else, what we do here is spread the signposts apart while changing each one as little as possible. The maximum separation and minimum distortion of meaning. So one more thing we need to do is our prompt engineering, and it's most boring part in this talk, so I will skip that. So we need to slightly change the word phrase to improve the performance. Okay, so here is the experimental setup. We use two public benchmark dataset, SumDD and StateFront, and we use our off-the-shelf CRIP as our backbone network, but we do not train anything. And we compared with this with a drive CRIP naive zero-shot settings thing, and metrics here, but I will come back to that later. Okay, so next, where are we? First, this is a geometry actually input. Here is the same kind of map as before, and on the left, the naive approach, the picture you have already seen. So clusters by drivers, and captions collapse into one position. And on the right-hand side, after double decoupling, the colors that is correspond to the behavior now form the coherent classes, regions. And 10 caption markers, I think it's very hard to see, but it's on the almost middle of the each corresponding clusters. So in other words, the map now looks much closer to the idea I described earlier. Islands of behavior, each with its own signpost. What, not who. And better geometry does translate into better accuracy. So across every metric and both dataset, our method outperforms the baseline. But you can see number here, but I move it quickly because I think the result on the next slide matters more for you. Okay, so for a real warning system, though, the 10 class accuracy is not the question you would ask. You would ask something more simpler. Is the driver safe or distracted? So we also evaluate the model as a binary classifier. And here's the result I personally find more important. The critical error in the warning system is false negative. A distracted driver whom the system judged as safe. That is a case where the warning never sounds. So with the naive approach, the false negative rate on SUMDD is 32.6%. That means roughly one distracted driver in 3 is missed by system. So with our method, it drops 10.9%. So it means that roughly 1 in 9. So still not perfect, but going from 1 in 3 to 1 in 9 with no training data, no extra hardware is, I believe, a meaningful step for safety application. So let me zoom out and conclude my talk. What I show you today is one instance of much bigger question. Can multimodal AI understand human behavior without large task-specific datasets? For distracted driving, the answer seems to be yes. But cameras and captions are only the beginning. The natural next step are to combine in-cabin camera with car signal. So, and driving context, and to move beyond distraction towards richer states, the workload, fatigue, risk, intent. And this is exactly where I need your expertise. So I can build the detectors, but human factor research is what tells us which behaviors actually matter for safety. So how drivers respond to warning and what a system must never get wrong. So AI gives us a scalable eyes. Human factor gives us judgment about what is worth looking at. That is why I am here at Lakpala, and I'm delighted to continue this conversation with any of you after this talk. So thank you very much for your attention.